Okay guys, welcome back. So this is a continuation of the last video where we looked at types of matrices, and in that video we discussed we ended with the symmetric matrix. Now in this video we are going to be looking at the skew symmetric matrix. So we said for a symmetric matrix, that's what we did last time, that the matrix is actually equal to its transpose. When you transpose the matrix, it will look as though you've done nothing. That's what we said about the symmetric matrix. But in this video we are going to be looking at the skew symmetric matrix. Now for a skew symmetric matrix, there are basic conditions that should be satisfied. Number one, every element of the principal diagonal is going to be a 0. So you have examples of skew symmetric matrices to be something like this. You can see the elements of the principal diagonal, they are all actually equal to 0. This is 0, this is 0. This is also a skew symmetric matrix, all elements of the principal diagonal are 0. This is another skew symmetric matrix, all elements of the principal diagonal are 0. But that's not the only thing that needs to be satisfied for a matrix to be called a skew symmetric matrix. Something else we need for a matrix to be called a skew symmetric matrix is this: that when you transpose a matrix, if I take the measure and I transpose it, it will look as though I just multiply the matrix by a negative sign. Okay? When you transpose the matrix, it will be the negative of the matrix itself. So in general, if you don't want to put it this way, another way we put it is that this is the same thing as you saying Aij. Okay? When you look at the i's and the j's, the entry at the Aij column or whatever element, that is going to be equal to the negative or Aji. So Aij is equal to negative of Aji. So what that basically means is this. For example, if you look at this is A11. Okay, so we are not going to bother ourselves with those ones. So let's look at it. This one is A12. This is A21. Okay, so you can see A12 is negative of A21. Or let's look at this something like this. This is A13, right? This is 13. And where is A31? This is A31 or C31. You can see A31 and C31 and C13, they are basically negative to each other. Or let's look at it. This is A21 or C21, C12 rather. This C12. So where is C21? This C21. I can see one is negative of the other. So those matrices are called skew symmetric matrices. Okay. So if I look for the transpose of this matrix, so you go ahead and study the transpose of the matrix. Again, I said we are going to come up with videos on that, but you can go ahead and move ahead of me to study the transpose. Well, you've gotten the whole concept from the last video. Take a row, make it the column. Okay. Or make a column a row, and that becomes the transpose. But I'll still expatiate on that. So this is what you call a skew symmetric matrix. The transpose of the matrix is equal to the negative of the matrix, or the entry at Ij is equal to the negative of the entry at Ji, and that's a skew symmetric matrix. So anywhere you're confused, you can go ahead and reach out and I will explain more. Okay. Now next we have what we call a dense matrix and sparse matrices. Now these are concepts that are used a lot. They are used when it comes to programming or when it comes to your computer system. Dense and sparse matrices, they help in memory optimization. Okay, they try to use them to store items in memory so that the amount of memory occupied is going to be far too less, especially the sparse matrices, not even a dense matrix, because dense matrix is something we don't look out for. Okay, so now what do you call the dense matrix and what do you call the sparse matrix? For dense matrices, a matrix is said to be a dense matrix if it has more of non-zero values compared to zero values, but it's a sparse matrix if you have more of zero values compared to non-zero values. So now here there is no what should I say, there is no it's not a must, so to say. It's not a must that the matrix must be a square matrix. In this case, it can be any type of matrix. Okay, though I think the examples I use are actually square matrices, but it mustn't be a square matrix. Now this matrix I have here, you can see it has more zeros compared to ones. So these are an example of a sparse matrix. Okay, these are an example of a sparse matrix. This other example I have here, this one is having more non-zero values than zero values. So these are an example of a dense matrix. We have another one. This is going to be an example of a sparse matrix because it have more zeros compared to non-zero values. So this is an example of a sparse matrix. So now there is what we call sparsity of a matrix. It's something you can always compute for. When you have a matrix, you can compute for the sparsity of the matrix. Now the sparsity of the matrix doesn't mean that the matrix is sparse. Okay, it means, okay, what's that value that will make this matrix to, what's the range of values, so that I can say this matrix is actually a sparse matrix or a dense matrix. So density and sparsity of a matrix is associated to both dense and sparse matrices. Now sparsity always lies between 0 and 1. So we're going to end this video here. In the next video we'll talk about sparsity of matrices. We'll go in depth into it and how we can compute the sparsity of a particular matrix. Okay, so I'll see you guys in the next video. Bye bye.